Finally, we need to talk about the derivative of the natural log of x. So the natural log of x has a shape that looks like this. It comes up. It's not defined for negative numbers or 0, so it approaches this asymptote here at x equals 0. And when you graph the derivative, it turns out that the derivative, if you look at every point and you approximate what's happening, looks like this. So when you check these points and you start plotting them and you look again for a formula, what you find is that the derivative is actually 1 over x. So the derivative of the natural log of x is 1 over x. That's our final formula for what we're going to call the basics chart. Now, the basics chart is not called basic because it's easy. It's called the basics chart because it's foundational to the rest of the work we're going to be doing. As our derivatives start to get more and more complicated in the future sections, everything is going to break back down into the derivatives on this chart. So you're going to need to make sure you know these derivatives very well. Take the time to memorize them, to work with them, and to feel comfortable with how these formulas work. Now, in addition to just adding these formulas to this chart, you should also know that the other rules also apply for these new derivatives. So the constant multiple rule will apply. So if we multiply a constant times one of our functions, then that constant will multiply the derivative. Also, the sum and difference rule applies. So if we have functions added or subtracted, we can still take the derivative of each term if some of those are exponential or logarithmic. And finally, the second derivative process is also the same. So to get the second derivative of an exponential or logarithmic function, we'll take the first derivative and then use the same rules to take a second derivative on the first derivative. So let's try some examples. Example 2. Use the formulas to find each of the following derivatives. So for the first one here, we're going to be able to go term by term because again, the sums and difference rules also applies here. So when going term by term, the first term is 5 to the x. We said with an exponential function, you get the same thing back times the natural log of the base. So the derivative of that first term is 5 to the x times the natural log of 5 minus the derivative of the natural log is 1 over x plus, now this last term we have 2 times 3 to the x. So we're going to use our constant multiple rule here. So that means that 2 is going to multiply the derivative of 3 to the x. So we have 2 times 3 to the x times the natural log of the base, which is 3. So our full derivative looks like that. Let's do part B. So the derivative here, again, we can go term by term. The first term here is e to the x. We said the derivative of e to the x was e to the x. 3 times the derivative of the natural log, which is 1 over x. So this last term, just so you know, we could write as 3 over x because we can multiply the 3 into the numerator. It means the same thing. Part C. So here again, we're going to go term by term. And we're going to start with this 10 to the x. The derivative of 10 to the x is going to be 10 to the x times the natural log of 10 plus, now here we have 5 times the natural log of x. So we're going to have 5 times the derivative of the natural log, which is 5 times 1 over x. So finally, for our last function here, we're going to go again term by term. The first term is e to the x, and the derivative of e to the x is e to the x, plus the derivative of 6 to the x is 6 to the x times the natural log of 6, minus the derivative of the natural log, which is 1 over x. Hopefully, you're starting to feel comfortable with this practice. So let's look at another example, and now let's also try some second derivatives within that. Example 3. If f of x equals 2 to the x plus e to the x minus x to the 2/3 minus the natural log of x plus 6, calculate the following giving an exact answer. So we talked a little bit before about this, but exact answer means we're not going to be rounding any numbers. So we're not going to be plugging things into our calculator to get a final answer. So let's start by finding the first derivative. So the first derivative of this function, I can go term by term because they're separated by addition and subtraction. So the first term is exponential. So my derivative is 2 to the x times the natural log of 2 plus the derivative of e to the x is e to the x minus, now x to the 2/3, remember that the power comes down and then we're going to subtract 1 from the power. So 2/3 x to the negative 1/3 minus, now 1 over x is the derivative of the natural log. And I'm going to write plus 0 because the derivative of 6 is 0. 6 is a constant. So just to remind us that we actually took the derivative of that, I'm just going to leave that here for now. And then we want to find the derivative at 1. So that means we're looking for the slope of the tangent line of the original function at 1. And we can find that by plugging 1 into our derivative function. Since we're looking for an exact answer, we are not going to simplify anything. So 2 to the 1 is 2. So I have 2 times the natural log of 2 plus e to the 1 minus, now here if you plug in 1 to the negative 1/3, you get 1. So 1 times 2/3 is 2/3 minus 1 over 1, which is 1. Now the only thing I'm going to do here is I'm going to combine my two constants. So the first term stays 2 natural log of 2 plus e to the 1. And I have minus 2/3 minus 1. So that's going to give me minus 5/3. So my final answer in an exact form looks like this. I don't have to write the 1 power of e. I could just write e and it would be the same thing. But here I'm writing it just so I remember that it's no longer a function and it's now a number. Now let's check out the second derivative. So again, we go back to the first derivative and we want to take the derivative of each term that we had in our first derivative. Now let's start with 2 to the x times the natural log of 2. We have to use our constant multiple rule here because our function, 2 to the x, is multiplied by a constant, natural log of 2. So that means that we're going to take that constant, the natural log of 2, and multiply that by the derivative of 2 to the x. The derivative of 2 to the x is 2 to the x times the natural log of 2. We'll talk about that in a minute. Plus, now the derivative of e to the x is e to the x. Now here, the next term, we have a negative 1/3 power. That's going to come down and multiply the minus 2/3. So that's going to make it a plus, and it's going to be plus 2/9 x. Now we subtract 1 from the power, so x to the negative 4/3. And then finally, we have to deal with this term here, this minus 1 over x. So remember that we can rewrite this as minus 1x to the negative 1. We can bring that x up by changing the sign of the power, which means when we take the derivative, the negative 1 is going to come down to multiply the minus, giving me plus x. And now here I'm going to subtract 1 from the power, so plus x to the negative 2. So here I have my second derivative, and what I want you to notice is that in the first term, I have a natural log of 2 times another natural log of 2, all within that first term. So I can write that as the natural log of 2 squared, because when I plug in a 1 here, I'm still looking for an exact answer. So I'm going to write the natural log of 2 squared, there's 2 of them, right? 1 here, times 2 to the 1, which is just 2, plus e to the 1, right? Plus, now if you plug in a 1 here, 1 to the negative 4/3 is 1, times 2/9 is 2/9. And if you plug in a 1 here, 1 to the negative 2 is 1. So again, the only simplification I'm going to do is going to be to add these two constants together. So we have the natural log of 2 squared times 2 plus e to the 1 plus, now 2/9 plus 1 is going to give me 11/9. So my second derivative at 1 looks like this. Again, if you wanted a numerical answer that was rounded, you could plug this all into your calculator and approximate to a certain number of decimals. But this particular problem wanted an exact answer, so we're not rounding anything, and therefore we are not going to turn our irrational functions into numerical answers. Let's try another.